Up to now in physics, our study of motion or movement has been limited to a study of position versus time and speed versus time. Newton wondered about this as well, but he didn't look just in terms of position versus time and speed versus time, but wanted to know the whys and the hows of motion as well. How does an object speed up when you push it? Why does an apple fall from a tree? Why does it look like astronauts float in space? For nearly 2,000 years, from 3000 BC up until the time of Newton and Galileo, studying the natural world was more of a philosophy than a science. Aristotle sought to explain the world around him by observations and then ideas that sounded good, rather than using tested methods or the scientific method to try to prove a theory or a law. Newton's first law is most often summed up as an object in motion stays in motion and an object at rest stays at rest unless acted on by an unbalanced force. Let's take apart that statement a little bit. Okay, let's talk about the idea of changing an object's motion. Okay, what's meant by changing an object's motion? That's pretty obvious to us. If we have an object that's standing still and we'd like it to start moving, that's a change in its motion. But what may not be so obvious is the object that is already moving. And so motion is that idea. Let me get back to our pointer options. Okay, that if an object is moving, it'll continue to move in the same direction at the same speed. But how do you get that to happen? Here we have the example of, we've got a golf ball sitting here. Okay, how are we going to change its motion? Well, you hit it with a golf club. The contact between the golf club and the golf ball, a force, causes a change of motion. Let's talk about what a force is. Okay, a force, as it says here, is any push or pull or action that has the ability to change motion. And really we can take these forces and break them into two major categories. One is contact forces, those things that actually need two objects to touch. Let's see, if I were to slide something or tie something or pull on something, I need actually two objects to touch. Friction is an example of that. Pushing on a bike or pulling on a rope are all examples of that. And the other are non-contact forces, or those forces that can act at a distance. The most often force that we'll see like this is gravity. I don't actually have to be touching the earth to feel the pull of earth. The two that we would end up working with in this class also are electrical or electrostatic forces, and the other is magnetic. Okay. And now how are these forces created? And they're created by the interaction between two objects, and that's an important thing about forces. It always is between two objects. You know, for one, if I let's see, have a golf club and I hit the ball, there's a force between the two of those. If I end up having, let's see, gravity is pulling me down, that's an interaction between me and the earth. Or this one here, on a windy day, I can feel the air trying to change my motion, or particularly on a sailboat, because a lot of air is running into the sailboat. Okay. And forces are required to change motion. If there were no force acting, an object would continue to move along. We may think that, hey, I'm rolling a ball across a table. Why does it slow down? There's a little bit of friction there that's actually slowing the ball down. And this is actually a big hurdle to overcome once you understand the idea that a force is required to change motion and not that a force is required for motion. That's something that Aristotle thought, that to go faster, or the more force you applied, the faster something went. As we'll find out, the more force we apply, the more acceleration we have. But once we get up to speed, if we have balanced forces, then an object will continue to move at that same motion or same speed. Okay, we see here this paragraph here covers that same idea we were just talking about. If we do have a ball that's moving, how are we ever going to stop it? And we actually need a force in the opposite direction. Generally, this will be friction, but if it ran into a wall, the wall would apply a force to the ball to stop it. And like we mentioned before, here's kind of the classic definition of Newton's first law. An object at rest will stay at rest, and an object in motion will continue in motion with the same speed and direction unless acted on by and I'm going to add something here, unless acted on by unbalanced forces. And we'll talk a little bit more about what's the idea of an unbalanced force. But you can probably get a pretty good idea. If I put something on top of a table, I have gravity pulling something down, and the table is pushing back up on that object. Those two things are balanced, and that object at rest will remain at rest. And that property of an object resisting change is known as inertia. And how do we measure inertia? Well, inertia is an object's tendency to stay still, or if it's moving, to continue moving. And so we can almost think of this as an object's laziness. I want to keep on doing what I've been doing. And you can think of an object that, let's say, a massive object like a mountain or a car, okay, is going to be much more difficult to change its motion than, say, a feather or a dime. Okay, so the more massive, the more lazy it is, or in other words, the more inertia it has. Okay. And so you can see here that Newton's first law is sometimes called that law of inertia, because the more massive an object is, the more it wants to stay where it is. And so I just use the word massive. How can we actually measure inertia? And that's in terms of mass. How much stuff is there? Objects that have a lot of mass, like we're saying over here, like this bowling ball, okay, has more mass or more inertia than, say, a golf ball up here. We end up looking at the two, that this bowling ball has a mass of about 5 kilograms, where the golf ball has a mass of 0.05 kilograms. Another way of saying that is 50 grams. The bowling ball has 100 times the mass of the golf ball, meaning it's 100 times more difficult to move. Just want to take a few moments for you to notice this gram call out and kilogram. If I want to convert between the two, okay, I can see that the prefix kilo means 1,000. So a kilogram is the same as 1,000 grams. They end up meaning the same thing. So if I want to convert between the two, I can go from kilograms to grams by multiplying by 1,000 and changing my kilograms into grams. The other way works too. We've talked a little bit about the idea of force as being a push or a pull, and with like any value that we have in physics, we have to have some type of a unit to describe this. And the unit of push or pull that we're probably most familiar with is something called the pound. To give you an idea how much a pound is, the pound is really the weight of a 16-ounce bottle of water. The book here describes a little bit about where pound comes from, and I had not known this before as well, that the abbreviation LB for pound, okay, comes from the Roman unit of libra, which means balance, and that pound comes from the word pondus, which means weight. Rather than using pounds in physics, most often we'll end up using the unit of a Newton, which is the metric unit of force. If you want to get an idea of how much a Newton is, think of the weight of a small apple. There's an old story that the way that Newton thought of gravity was that he was sitting under a tree and an apple fell on his head, And he ended up saying, oh, hey, what caused the apple to fall out of the tree and what keeps the planets in orbit around the sun must somehow be related. So think of the apple as being, a small apple as being the weight of 1 Newton. Now, as we get a little further along, we start talking about unbalanced forces and the change in motion. We'll define the Newton in terms of how much motion it causes a change. And you can see here in the text where it's talking about if I push with a force of 1 Newton, I can change the motion of a 1 kilogram mass by 1 meter per second after 1 second. But we'll get to that in a little while. Right now we're talking about Newton's first law, where we're worried about objects either at rest or in motion where the motion does not change. And just one last thing about net forces. And we'll talk a little bit more about that later. When we have multiple forces that are acting on an object, we can just add up the forces in the various directions to come out what the net force is. You know, the word net you'll hear sometimes in business about, like, what's the net profit of a company? Net is after you've paid all your bills and received all your money, how much do you have left over? Okay, same thing with forces. This one, if everyone's pushing in the same direction, I'm pushing with 300 newtons to the right and someone else is pushing with 300 newtons to the right, my total force is 600 newtons to the right. But let's take a look at, you know, this box here. Okay, we have gravity pulling it down with a certain force. We have the floor pushing up with a certain amount of force, and the magnitude of those ends up being the same. They're in opposite directions, so we have this net force of 0. And as we might expect, the box that's just sitting on the ground will remain there unless we have these two guys come along and start giving it a push. But because they're balanced forces, and that's something that we'll be talking about in this unit, is net when the net force equals 0, it's a balanced force, or balanced forces on an object. And it meets Newton's first law. And as a bit of a check for your own understanding, go ahead and check these 3 things about stating Newton's first law, how is mass related to inertia, and this last one, what is net force and how is it determined?